So I
There. Thank you.
Da is a senior applied scientist at AWS AI, and he leads several projects, including the Deep Graph Library and DGL. He is an expertise in the distributed training of graph neural networks. And today, Da will introduce some of his recent work on system side and algorithm side for accelerating and scaling GNNs. So,
yeah, great. Thanks for coming, Da. Again, like it's really great to have you present here in our group meeting. So thanks again. Looking forward to it. Been looking forward to this. Yeah.
Thanks for the invitation. Actually, it's really nice to have this opportunity to talk to you guys. But one question: how do I enable shares?
Oh, sorry.
Yeah, I think you got it.
I have enabled. Try again.
Let me see. Okay.
Great.
Okay.
Yeah.
Can everyone see my screen?
Yeah, we can see it.
Okay. Cool. Yeah. Okay. Yeah. Thanks again for the invitation. It's really nice to have this opportunity to talk to you, guys. So yeah, again, my name is Da Zheng. I'm a senior applied scientist here, and today's topic is on about our recent work on large-scale GNN training with DGL. Let me see. Okay. So as we know that a graph have been used in many applications, and we want to generate business values from the graph data. So we would like to apply graph machine learning techniques on those data. So we have many applications here. I just show you a few examples. So for example, in social network, we would like to use a graph machine learning technique to identify influencers or bad actors or moderate content, or in e-commerce, which is very important for Amazon. We would like to use the graph ML for a recommendation, product ranking, like ad targeting, and so on. And then also in the knowledge graph, in the case of knowledge graph, we want to use the graph ML for identifying the missing information and answer questions, and so on. So in any of those applications, actually, for the real world graph, they are all very, very large. People keep telling me that they have a graph of like billions of nodes, what they are going to do. As we all know that today, one of the most popular techniques for graph machine learning is graph neural network. And we actually have seen, in this chart, this chart is a little bit old, but we can clearly see that the trend is very obvious. And we see the number of publications about the graph neural network has really soared since 2017, like 4 years ago. And I also see in researchers from both industry and academia trying to apply these techniques in many applications, and we have seen very promising results. Here is a very general introduction of graph neural network and how a graph neural network is formulated. So in general, we can see, I think a graph neural network is as a message passing. So in this formulation, each node will send a message to their adjacent neighbors, and then each node will aggregate all the messages from its neighbors, and then use those messages to update its own representation. So, in this, the process of the message passing can be customized with 3 functions. So on each edge, we can define a message function to generate a message, and then on the node, then we can define a reduce function that is to aggregate the messages from their neighbors, and then we define a node update function that can merge the aggregated and the messages to the target, to the node, and then update the node representation. And we can stack multiple message passing. So in this way, a node will receive the. So previously, the message passing works on the direct neighbors. So if when we stack multiple message passing together, then a node will receive data from multiple hops away. So this is usually how a GNN works. And we will see later that why this multi-layer GNN actually causing making the GNN training on large graph very difficult. So we in AWS we develop DGL to simplify GNN model development and to enable GNN training efficiently at a large scale. And here just show you the full architecture of DGL. We can see that DGL actually sits on top of any existing deep learning framework, such as PyTorch, MXNet, and TensorFlow. And then inside DGL, we implement those highly optimized sparse graph operators in C++, and then provide users a friendly Python API for any GNN operations. And in addition, DGL on top of DGL, we implement some domain specific packages such as DGL KE or DGL Life Science for various applications. And in DGL, the main programming interface will be like a graph. So basically, DGL provide a graph class for users to express graph neural network models. And then the graph class is actually the core of the DGL programming interface. And we provide an easy and consistent way to access graph data and express any desired computation. And then the main API is actually this, we call it update all function that allow to allow user to perform message passing computation. And then when users call this function, then user can customize the message function, the reduce function, as well as the node update function, as we have seen in the previous slide. So as I said earlier, that most of the real world graphs are actually very, very large. They are all at the billion scale. So in practice, one of the biggest challenges for us to train a graph neural network on large how are we going to apply a GNN on a graph of that size. So potentially we can perform like a full graph training in GNN. So this is something. So this means we are going to perform the GNN computation on the entire graph during the training. So basically we are going to take the full for this training method. We basically take the full the adjacency matrix of the entire graph, and then we apply the graph neural network models to compute the node embedding. And if this is a multi-layer GNN, then we apply this multiple graph neural network multiple graph convolution network on the entire graph. So in the era of deep learning, this may sound very strange that because why people still care about this full graph training method. But in practice, this training method actually is used when the GNN model was developed initially, and then many GNN frameworks actually are designed for full graph training. But the problems of full graph training is also very obvious, right? So we needed to, the amount of memory consumption for full graph training is proportional to the number of nodes and number of edges. And this can easily get to like terabytes of data. And then it's very easily we will run out of memory. And even if the memory is not an issue, because I have seen people develop distributed GNN training framework for a cluster of machines. So this may potentially address the memory issue. But the other problem I have seen is that the full graph training will also make the convergence much slower. And so here is the benchmark I run on different a graph of different sizes. And you can see that when the graph is getting larger and larger, the gap, the training speed, the gap of the training speed between full graph training and mini-batch training is in the order of tens or 100 times. So basically, full graph training is maybe can go like can be like 100 times slower than the mini-batch training.
Why?
And also, I've noticed that for a very large graph, those full graph training method will also potentially generate a lower model accuracy. So now the question is, that all being said, what in practice what we should use is mini-batch training, and this is just like many other the training method we usually perform for deep learning models. Now the question is, how are we going to perform mini-batch training on GNN? So unlike any other deep learning models, the data in a graph has dependency. So basically, you can see the nodes are connected, right? So because of this, we can no longer sample data in an IID fashion, just like we do for other deep learning models. So as a result, here it just shows you one way of how potentially we can sample a mini batch in a graph. So in the case of node classification task, what we usually do is we first sample target nodes from the training set where our model will make our prediction, make a prediction, and then we sample the neighbors of those target nodes. And for the multi-layer GNN, we will sample neighbors multiple hops away, as shown in this example. This is a two-layer. This is a mini batch we sampled for two-layer GNN.
Can I ask you a question here?
Sure.
So this all makes sense to me. One thing that would help me is to make it a little bit more concrete. Like, what's an example of a problem or a classification problem we would be training on a graph? So like this might be a social network, and maybe we're trying to classify node 1 as like a I don't know, like what do you have an example of, like, what can we map a concrete problem on top of this just to make this concrete?
So if you want to assign a label, so for example, in the social network, if you want to assign a label to a user, right? I don't know what kind of, depending on your task, right? So let's assume that we just want to assign a label to a user. Then we want to use this user's friends and their friends to help us to make this prediction.
Right. Okay.
Right. So then the target node is where the user we want to make a prediction, the label, and then those neighbors will be the friends of this user.
And then is the training data just one giant instance of the graph with all of the labels applied?
Yes, yes.
Okay.
So we assume here that the graph is all the nodes are, sorry, not all those nodes are connected, right? So this is one graph.
Okay.
And we want to make this kind of prediction, and then we need to generate a mini batch from this large graph.
I see. Okay.
Right. So basically, yeah. So I mean, to generate a mini batch from this large graph, we will sample to make a prediction for one node. We actually need to sample their neighbors and potential neighbors and so on. So that means for one node, we actually need to sample many. The mini batch will involve many more nodes. So in the end, the number of neighbors or number of nodes in a mini batch will grow exponentially with the number of layers. This is the main problem of the main cause of it is very expensive to train GNN models on a large graph. Because when we need to access so many neighbors, that means we need to access a lot of data, right? For just the one mini batch. And also that the computation there will be much more computation involved in this mini batch just to make a prediction on one node. So so in this talk, I'll discuss the work we have done to enable efficient mini batch training from two perspectives. So first, I would like to talk about our development in the infrastructure. So that is we are developing a framework on top of DGL called the dist DGL to enable distributed GNN training on a large graph. And in this work, we try to explore only the system level optimization. We want to see to what end we can really optimize the training speed. Then my observation is that pure system level optimization is usually not really efficient. Is not sufficient to address all the problems in GNN training on large graph. So therefore, we also need to seek all kind of innovation in the algorithm design. So in this talk, I would like to talk about our neighbor sampling algorithms as well to enable more efficient training in the context of hybrid CPU and GPU training. So basically, we want to, when we train a GNN model, there will be data stored in CPU, and then we want to perform the computation in GPU. Okay, so first, let's I will cover our design on this DGL framework. So we started to work on this DGL more than 1 year ago, and we have developed 2 versions so far. So the first version was released last August, and then that version was mainly optimized for CPU training. We later extended the design and optimized this DGL for hybrid CPU and GPU training. And this version is still in the stage of prototyping, so we don't have released the code yet. So in the following talk, I will refer to the version that optimized for CPU as this DGL v1, and then refer to the version for the GPU as this DGL v2. And in both versions, we actually are facing the same kind of challenge in distributed GNN training. So basically, I can see there are 2 major challenges. So first, there is a lot of data movement due to the neighbor sampling algorithm we have seen previously. And so in this case, we need to really reduce the data movement as much as possible. And then the second challenge is the load balancing. So because of the neighbor sampling algorithm, then the mini-batch we generated on each CPU or on each GPU may have different sizes. So basically, a mini-batch, the mini-batch from different CPUs or GPUs will have different number of nodes and different number of edges. So in this case, this will potentially will have different amount of computation and different amount of data movement on each trainer, on each GPU. So because of these challenges, and so overall, our 2 versions of the DGL will share the similar design. So in this DGL, we will first partition the graph with mean edge count and store the partitions on different machines. And then during the training, and all machines will have run the same components to parallelize the training computation. And we want to use we use the data parallel to distribute the computation. In the DGL framework, we basically identify 4 components. So we have this GNN training component that will get the mini batch and then perform the forward and backward computation to estimate the model parameters. And then we have the sampling component that is to generate a mini batch from the cluster of machines. And then we also have this KV store component that will store the data, the node data and the edge data for the entire graph in this cluster of machines. And then the trainer will, when trainer get a mini batch from the sampling component, it will try to fetch the node data and the edge data required for this mini batch. Once all the data is ready, then it will perform the forward computation and backward computation. And the other component is this the gradient. So we need to have one component to aggregate the gradient for the model, and this part is the very standard component, and we are just using any deep learning framework. So another thing I want to mention is that we want so to enable, to have a more reliable training, we actually use a synchronized SGD to aggregate the gradient from different trainers, and this will cause some kind of load balancing issue because different mini batch are different sizes, right? So and we because of the synchronized SGD, we are actually putting a barrier in the end of every mini batch iteration.
Can I, before we move on, can I ask how exactly do you partition? Oh, maybe you're about to show that. Sorry.
Yeah.
Sorry.
So, yeah. So the first thing is, how are we going to partition a graph? So many people design. So far, what I've seen is that most of people will choose to use kind of like a random partition or something like that, because they think it's more advanced partitioning algorithms are very difficult to actually execute, and it cannot scale to a large graph. This is whether or not that argument is true. I think it's debatable, and we choose to use more advanced graph partitioning algorithm simply because we really care about the data locality. We want to reduce the data movement as much as possible. So basically, and we use this, we actually use a very lightweight version of MITIS to partition a graph. And then we, basically the MITIS will assign nodes to partitions, which that results minimum edge cut. And then we use generate partitions based on the MITIS, we split the graph based on the MITIS partition result. And when we use the MITIS when we generate, when we generate the physical graph partitions, we actually also duplicate some nodes. We call it them hollow nodes. This is just simply to help us to speed up the distributed sampling. Another very important thing is that when we partition a graph, we try to enforce some load balancing criteria because as I mentioned earlier, the two challenges we are facing in distributed training. One is to reduce the data movement. The other one is to ensure the load and balance. So the way we have multiple strategies to ensure load balancing. The one thing we are doing is we try to balance the partitions when we partition a graph. So here we only use the two simple criteria to balance the partitions. One is we want to balance the number of nodes for each node type, and then we want to balance the number. We balance the in degree of the nodes for each node type. So the second one is basically try to balance the number of edges of each type of each relation type for each partition.
What are the different node types here?
Yeah, so so the node type means we needed this DGL is designed for heterogeneous graph. So in practice, most of the real world graph actually are heterogeneous, meaning you have different node types. So your graph may have like a friends. Graph may have other like nodes like I don't know. I just need to make something up. So social network is more a good example of like homogeneous graph. But for example, Amazon graph will have like users, you have buyers, you have sellers, you have
Right.
products, they have reviews, and you have all different kind of kind of nodes you form in a single graph, right?
Yeah.
So many graphs are like that. So the DGL is trying to design to work for heterogeneous graph.
And is it because you might use different like message passing and update and aggregate functions on each of these different types?
Yes, different. So if a node have for different node, different type of nodes, we may define different neural network models, different neural network models with different parameters, and also for the different different edge types. When do we do the message passing, right? So we may use different message functions.
I see. Okay, thank you.
Yeah. And the other thing we can take advantage of this different for different node types is that when we generate a graph, we for any machine learning model, we need to split the data, your label data as a training set, a validation set, and the test set. We can consider them as different node type.
Oh, interesting.
And also the node type, because we want to balance the training set. We also want to balance the test set, right?
Oh, so okay, I think this is okay. So training set, test set. In this case, is it just we have one graph and we have to partition it into a training partition and a test partition?
So I mean, like this training. So this kind of data split is like usually we do for any machine learning model, right?
Yeah.
So for any machine learning model, when we train a model, we need to get some label data out and use them to train the model.
Right.
And then we need some data out to help us to select the model. Right. And then some data for us to finally evaluate the model quality.
Right.
Right. So we found in practice, I mean, to balance those different sets are very, very important. Otherwise, otherwise the model training will be very imbalanced.
I see. I think I'm asking because I'm having trouble moving my traditional knowledge of like CNNs to graph neural networks, because I understand like in a CNN we have a data set. Let's say we have a data set of 1,000 images and we split it into like 80% training image, 10% validation, 10% test images. Every image has a label. That I can my brain understands that. I guess I'm still having trouble understanding like what the data set looks like for a graph neural network.
I can give you an example that we have a single large graph and we mark some of the nodes as training set, some of the nodes as validation, some of the nodes as test.
I see.
And when training, we mask the labels of the validation or test.
Okay, that makes a ton of sense.
Yeah.
Okay, and so this what you're talking about here is basically you can't just put all the training data in one place. You need to spread it. You need to spread it throughout.
In this case, there are many of nodes, so you need to split partition the graph into nodes in the cluster.
Yeah, I imagine that's both for load balancing reasons and also for training performance reasons. Like if you don't sample your training set well, you just won't train well. Just as if you didn't sample.
Yeah.
If you sampled a
I think so.
non-representative set of images for a CNN, you'd train poorly.
Mm-hmm. Yeah. Okay. So actually, in the case of graph, in the context of graph, there's another thing. It's very different from CV or NLP. Is that when you have a graph over like 1 billion nodes, right? So very likely that your graph may have only 1 million nodes with labels. The rest of the nodes actually have no labels at all.
Oh, interesting.
But then in practice, I mean, when for graph neural network, we actually use all those nodes for the training.
As in you use
those nodes are maybe neighbor nodes. The unlabeled nodes might be the neighbor nodes.
Interesting. How do you use an unlabeled node for training?
I mean, this is a general setting for semi-supervised learning, right? So in the semi-supervised learning, we want to use any nodes with labels as well as the unlabeled nodes to help us to train a better model.
Interesting. Okay.
Right. So that's why this the balancing the training set and on all the machines or on all the trainers, it will be very, very important.
Yeah. Great, thank you. Sorry for all the interruptions.
No problem. That's a good discussion. So here is just show you some our previous result on why this is important, and to reduce the data movement, with the medius partition, and also why it is important to enforce the load balancing, right? So for some data sets, if we just use the medius to reduce the edge cut between partitions, then we can get a speed up, and but if we enforce the load balancing, we can get some further speed up. This means the default medius partition actually will generate some partition result that is less balanced. However, in some other data sets, if we just ignore the load balancing criteria, then we are going to generate a partition that is very imbalanced, and then then the medius partition actually generates some. The performance will be even worse than random partition. But if we ensure that this load balancing when we partition a graph, then we can always get a much better speed up when compared with the random partition. And that's why the load balancing, to ensure load balancing, is very, very important. The other thing is that people keep telling us that, okay, we shouldn't use the medius partition because medius is very slow and it's not scalable. So actually, there is medius itself. There are different implementations of medius algorithm, and there is actually a parallel implementation of medius called the PAR-medius. And actually, we benchmarked it, and it's actually PAR-medius is pretty fast. Actually, it's pretty scalable. We can use many machines to partition a graph, right? So, and then I want to benchmark then how fast, what is exactly the computation overhead for medius partitioning, and in this entire training pipeline. So, first, even if we want to partition a graph, for every time we train a new model, we need to partition a graph. This is the worst case scenario, right? Normally, when in our design, we partition a graph once and then train the model many times, either for hyperparameter tuning or for different experiments or for whatever reason. This is a very common case. But even if in the worst case scenario, we want to partition a graph and then train the model once, and that's all, then we see the PAR-medius actually itself is not really the major bottleneck. It's still, the speed is decent. And also this is dependent on the task. So for node classification, the training set might be fairly small. Then the training speed is quite fast. Then PAR-medius may add some overhead. But if we talk about link prediction, in this case, we are going to use all the edges in the graph to train a model. Then the training is going to be much slower. And then the PAR-medius has still the same overhead. So in this case, anyway, in either case, we think PAR-medius is not, having PAR-medius is not really introduce a lot of overhead. Even if we do random partition, we still need to load the data into the machine and then split them, right? And we still need to construct all the physical partitions and etc. All those overhead are still there. So then let's move on to the actual design. How we perform distributed Zheng training. So in this DGL, we first it is designed for minibatch training, and then the second version of this DGL, basically this DGL v2 is designed for hybrid CPU GPU training. So in this case, that we want to store the entire graph, the graph partitions in the CPU memory, and then we will generate a mini batch, and then the mini batch will send to GPU for the forward and backward computation. So so because of our medius partitioning, and we co-locate the data, the graph partition data with GPUs, and then when we generate the mini batch, most of the data actually come from the same machine. So then we can avoid reduce a lot of data copy across machines. And inside this machine, we will inside each machine we will run all around the same, like the sampling servers and the KV store servers, and then each machine will also have the trainers, and as I explained earlier.
So can you go to the previous case?
Sure.
Case? Okay, so the trainer, sampler server, KV store server are on the same machine.
Right.
Okay, so what does the remote machine do here?
You mean, wait, this one?
Yeah.
Those are the, I mean, this is one machine, and
Yeah.
those are the other machines.
So it communicates both, it's both for sampling and synchronizing the features between machines.
I mean, so okay, so one thing I forgot to mention is this. So we partition the graph, right? But when we sample, but we say when we partition the graph, we do not really cut the edges. We will still store the entire graph data. There's no data missing. And then that means when we sample a mini batch, even though most of the data come from the local machine, I mean, because of the data, medius partitioning and the data co-location with computation, we still need to sample those neighbors that neighbor nodes that are actually stored in remote machines, because we do not really remove those edges.
Okay, so those are the hello nodes you mentioned, right?
Hello nodes, kind of, but it's more like hello nodes is just we use to indicate that there is a neighbor node that is actually stored in remote machine. But we just store this, have this hello nodes in the graph structure to indicate that. Otherwise, we don't know this, there is like a neighbor node in remote machines.
Okay.
Right.
Okay, that makes sense. Let's go ahead.
Right. Okay. So then the next question is, one question is why actually we really want this hybrid CPU GPU training. So because we have actually in this community, we have seen that people say, okay, so first, like, we have seen that, for distributed GNN training, we need to have a lot of like data movement. And so because of this, we may not really get, a lot of advantage of, computation power in GPU. And in this research community, we have actually seen that, some distributed GNN framework actually give up, using GPU for GNN training. The examples are some framework from Alibaba, basically the Euler and the AliGraph. But on the other hand, like, and graph neural network is still like any other deep learning neural networks, right? So it contains they contain many floating point computation, and then GPUs are still well suited for numerical computation because of the large degree of parallelism and high memory bandwidth in the GPU. So that's why we really, we think, even though there's a lot of communication overhead, we still think a GPU can be beneficial. On the other hand, we also, because the GPU has a very small memory, we cannot really store the entire graph in GPU. So we choose to store the graph data in CPU memory so that we can scale to very, very large graph. And because in this case, we are going to perform the mini-batch sampling in CPU, and then we need to do a lot of we need to gather all the node features and edge features in the CPU, and then we send everything to GPU. So we need to make sure any computation and any data copy in the CPU has to be very, very efficient so that we can keep up with the GPU computation. And to really take advantage of the GPU computation, we develop asynchronous mini-batch training pipeline to overlap the mini-batch sampling and the data gathering in CPU with the mini-batch computation in GPU. So in this example, so in this figure, we just show you an example. So when we perform, when GPU is performing the mini-batch computation for step 0, then the CPU should move on to sample mini-batches and get the data for the mini-batch of step 1. And then actually we don't just want to overlap the CPU and GPU computation. We also like to overlap the network communication, the CPU computation, CPU data copy, PCIe data copy, and the GPU computation. So this will require us to perform almost all operations in the mini-batch pipeline asynchronously. But because we are using synchronized SGD, so we will still have this synchronization barrier in the end of every mini-batch iteration.
Can I ask a question?
Sure.
So do you need to perform the graph partition for every step, or is the sample here means something else?
We perform, so the graph partition is done in the pre-processing step.
Okay.
So we partition a graph once, and then we will use the partitioned result in many trainings.
Okay.
But
So the sample here just means to get the partition result for each step.
So the sampling here means that we will try to generate a mini batch from a list of from all the graph partitions.
Okay.
Stored in the cluster.
Okay. Okay.
So it is like partition is a pre-processing stage that partitions the whole large graph into machines in a cluster, and sample is a local sampling, which means each machine samples a mini batch from its own partition graph.
I see. I see.
Yeah, I mean the sampling will try to generate sample most of the nodes and edges from the local partition, but we will also need to issue remote requests to the remote partition to gather additional neighbor nodes and edges.
Thank you.
And actually, the picture I show you in the previous slide actually is a very simplified version. The version actually is much more complex because we actually are building a very deep pipeline. So because we want to overlap many the mini batch computation for many mini batches to hide the latency of the data access and the CPU computation. We also like to use very deep pipeline to hide the imbalance in mini batch generation. Because remember that each mini batch for different GPUs will have different number of nodes and different number of edges. So it is very likely that there's some imbalance in the process of generating mini batches. So here I will just show some brief results we have done for this to benchmark this system. First, we compare this DGL with Euler. This is Euler is a distributed Zheng framework developed in Alibaba. We noticed that Euler actually is really designed for CPU. So we tried it on GPU and didn't see much speed up. I think the main reason is that it doesn't the way they parallelize the mini batch training is not really suitable for GPU training. It's more mainly designed for the parallelization strategy is mainly designed for CPU training. And then if we compare with Euler, we can get like 18 times the speed up. And we also try to compare our previous version and so basically the first version and the second version. And so the first version was originally really designed for CPU training, distributed CPU training. And we can see it's actually, it performs relatively well on GPU. So we can, if we compare the the CPU training and the CPU training and the GPU training, we can see the GPU training actually gets 4 to 15 times the speed up. But then if we deploy all the optimizations in the DGL version 2, then we can see additional speed up, 2 to 3 times speed up compared with the previous version. We also test its scalability. Roughly, if we have a more complex model, then we can get a relatively good speed up. So, for example, if we use more GPU to train like a graph attention network, we can get like 36 times speed up by using 64 GPUs.
Looks like the RDCN does not scale well as.
Okay, I guess this is a confused area. I should. Here's so RDCN is actually still get pretty good speed up. Actually, this is from 32 GPU to 64 GPUs. We get 2x times speed up. So the reason we only have 32 GPUs as a baseline result is the data set for RGCN is very, very large. We cannot run it with a single machine. So actually, we still get a close to linear speed up. In both cases, in the GAT and in RGCN, we get a somewhat close to a linear speed up. So it's just when
this graph, this figure is very confusing.
Yeah, I agree. So I mean, I was thinking, which maybe we need to move this line to somewhere.
So RDCN cannot work if you don't have 32 GPUs. The baseline is the 32 GPU.
Yes. I mean, either we use a very small data set to benchmark it. But anyway, so the reason we want to show this line is that there are data sets that is large enough that we cannot train with one GPU, one machine. We have to use multiple machines.
Okay.
Okay, so that basically that's all for our this DGL design.
So can I summarize the V2 compared to V1 as you use complex pipeline design to hide the latency between data movements and network communication, something like that, so that makes the training faster?
Yeah, so that is basically the most important stuff we did to accelerate GNN training on GPUs.
Okay.
But of course, I mean, like the partition graph partition part is also another factor that get
but this part
speed up the training. But those are it's the same for the first version and the second version.
Okay, good.
Right. So if no more questions, I guess I can briefly discuss what we did for our algorithm design, mini-batch sampling algorithm design. So again, we designed this algorithm is still mainly for this hybrid CPU and GPU training, where we store the graph data in CPU and then perform the mini-batch computation in GPU. I guess we have only 10 minutes left, right? So I can just briefly, quickly discuss the main idea. So again, so this is a review of the neighbor sampling algorithm we are using in the DGL, and this is the neighbor sampling algorithm actually most of the people are using actually. So the main thing that it does is that when we sample, on each node we will sample their neighbors. So we will use a small number of neighbors to approximate the original neighborhood. And usually this neighbor sampling is we sample neighbors uniformly at random. So that's why then this when we try to approximate the neighbor aggregation, this calculation is very simple. We just add all the sample neighbors, and then if the aggregation is average, then we just need to average over the number of sample neighbors, and that's all. And this neighbor sampling algorithm is trying to have this unbiased, when after we sample neighbors, we want to have an unbiased neighbor aggregation estimator. And for different neighbor sampling algorithms, a lot of times the people want to reduce the variance while we can still maintain this unbiased neighbor aggregation and estimation. However, this neighbor sampling algorithm has a very big problem, is that so because we have this exponential neighborhood explosion, then when we store the graph data in CPU and perform mini-batch training in GPU, most of the overhead is actually to gather all the data in CPU, and gather all the node data in node features in CPU, and then copy the node features to GPU, and then then we have some small amount of overhead for mini-batch computation. And for different graphs, that this overhead of gathering data in CPU and copy data to GPU can become very, very large. So for example, in this OAG data set, this data copy in CPU and from CPU to GPU actually accounts for like more than 80%, because this data set has very large node features. And so our algorithm is trying to add an additional objective, is to reduce the data copy between CPU and GPU. The idea is actually very, very simple. We want to cache some data in GPU, but if we just cache, if we just pick some nodes and cache them in GPU, the cache hit actually is very, very low. If we don't change the sampling algorithm, the cache hits I have experimented is if I cache like 10% of the nodes, most the frequent largest degree nodes, I probably can generate like 40% of cache hits. So that's not even, we cannot even reduce the data movement by half. So instead of like, the idea is that we want to change the neighbor sampling algorithm, and we will still cache large degree nodes in the GPU, but when we sample neighbors, we want to sample those nodes that we want to prioritize the neighbor sampling so that the neighbors we sample are already in the GPU cache. In this way, when we generate this mini batch, most of the nodes will already be in the GPU cache. So even and because of that, because we have changed this neighbor sampling algorithm, we do not really need to catch. We only need to catch a very, very small amount of data in GPU. So actually, in our experiment, is we just catch 1% of the nodes in the graph, and then we can generate very high cache hits and reduce the data movement. But of course, the problem is, okay, so here is, we tried a different strategy of caching nodes. So one thing is that I need to mention is when we construct, when we select the nodes for caching, we actually, the selection is not deterministic. Actually, it's randomness. We sample nodes, we sample nodes and put those nodes in the cache. And then we need to, because the nodes are sampled, then we need to define a distribution to for this node sampling. And we tried different strategies for this node sampling. Turns out the simple one, this node, the degree-based version actually is good enough. And then because we use degree-based, strategy, or you use degree to define the sampling distribution, then the node where we sample to put in the cache, different node will have different sampling probability, right? So that means when we sample neighbors, different neighbors will be sampled with different probability. Then if we want to still have, when we perform the neighbor aggregation, and if we want still want to have this unbiased neighbor aggregation estimation, then we need to adjust this neighbor embeddings when we perform this aggregation result. When we perform the aggregation operation. So that is the basically the modification we did to the graph neural network model after we adopted using this global neighbor sampling algorithm. And that is the main idea we did for this algorithm. And we actually experimented this algorithm in many different large data sets. And even though this algorithm is very simple, this actually generates a very good result. So first, we can see that this algorithm will doesn't really affect the model performance that much. It's the model performance between this GNS, and the NS here is just our baseline neighbor sampling algorithm. So these two algorithms have more or less the same performance. And then, but the speed, the training speed will be much faster. But if we compare this our GNS algorithm with other neighbor sampling algorithm, we can see that actually we either our performance is much better, so the model accuracy is much better, or our the training speed is also much better.
All right,
So,
can I ask a quick question?
Sure.
Do you have an intuition why your sampling algorithm performs just as well as the baseline compared to the other ones?
Right. So, I mean, our sampling algorithm is still a neighbor, it's very similar to this neighbor sampling algorithm, right? This NS. The only thing we change is we want to give the nodes that are already in the cache with higher probability. And those, because, I mean, we select those large degree nodes in the, we give the large degree nodes with higher probability to be in the cache, right? So most likely that, when we see,
I guess you would be prioritizing nodes that have a larger impact on the overall network. Does that sound right?
Sorry?
So when you say you're prioritizing nodes that have a larger degree into the GPU cache, isn't it basically biasing like your training towards nodes that have potentially larger impact on the network?
Yes. So basically, I mean, in this in this setting is given that they have generated a similar result. So that means we only need to use a small number of nodes in to generate to train a model.
I see.
And
Thank
but
you.
on the other hand, I think it's from each node, from the perspective of each node, we don't this node doesn't really see those nodes are those neighbor nodes are used by other neighborhood or not. Right? They from that node perspective, we just sample those neighbors, and then we use an unbiased estimator to approximate the original neighbor aggregation operation.
I see. Thank you.
Right, but on the other hand, so another thing we realize is for this for other methods such as these ladies or something like that, those models will those methods actually cannot really perform well on large data sets, because those methods tend to generate generate a mini batch with many nodes has empty neighborhood.
Oh.
So a lot of nodes will end up having no neighbors at all. So that kind of mini batch will have a very negative impact on the model performance. So on the other hand, if we sample enough neighbors for each node, we can train the model pretty well. But I think I understand. I guess I understand that the concerns in this matter, like people will think, oh, you are using just a small number, or a small amount of data for training the model. This may not work in some cases. That might be true, but we need to understand what kind of cases that actually doesn't work. So here is just the explanation of how we get this speed up, right? So we really can, our algorithm can really squeeze, this data, reduce the overhead of data movement in CPU and GPU.
Can I ask, so the baseline here is neighbor sampling. Yeah. Is that is that kind of the state of the art or standard? Did you choose it because that's what everybody does, is use this specific neighbor sampling algorithm, or
okay. First, yes, the reason we choose this neighbor sampling algorithm, even though this is the first algorithm people are using, it turns out this algorithm actually is very robust to all different settings. Okay. And especially this is probably the only sampling algorithm that is effective in a large data set.
Oh, interesting.
It might not be state of the art, but most ones.
I see.
Like
why is it? Okay, so so it works in large data sets, unlike, like you were saying, ladies, which has this issue on large data sets where it'll generate neighborhoods with zero neighbors.
Yeah, I mean, the ladies has a problem that on large data sets it cannot generate mini batch with all the nodes has neighbors.
Yeah,
and something like more recent sampling or training strategy that cannot scale to a large data sets for other reasons. So, for example, this lazy GCN try to generate a very large mini batch and then catch that mini batch. Sorry, it will generate a meta mini batch, and then from that meta mini batch to generate a mini batch. And it turns out this kind of method will also not scale to a large graph, because when your meta mini batch cannot be very large because the data meta mini batch is actually stored in the GPU. So because GPU memory is limited, so we cannot use a very large meta batch. And then if the meta batch is not large enough, then that model will not, that method will not work. So we actually tried, and it's not only slow, it also has very bad performance when the meta batch size is not large enough.
Yeah.
And so, I mean, although there are many, I mean, people have explored many sampling algorithms, and with our experience is that most of them do not work so well on large data set.
Okay, interesting.
So that's why we have to use the original neighbor sampling algorithm.
I see. That makes sense. Okay, and just this is a very basic question, but like you have to do some sampling. You need to pick some kind of sampling algorithm.
That's right.
There's no way to do this without sampling.
That's right. We have to sample neighbors. Otherwise, the mini batch size will be almost your, it will be majority of your graph.
Right. Okay.
Yeah. The sampling proposed in this paper is different from others. Is that it did minimal change to neighbor sampling.
Right.
The only change is that it prefers nodes in the cache.
It's just an intelligent way of, yes. Okay. Yes.
Right, and then we need to adjust the neighbor aggregation operation, but then that's all. The idea is really simple, but turns out it works pretty well. We were very surprised as well.
Yeah,
that's neat. It's very neat.
Can I ask 2 questions?
Sure.
So first, yeah, I'm wondering, like, is the MITIS sampling or partition you mentioned earlier works here or used here or not?
No, it's not used here. So ideally, we actually needed to combine this GNS algorithm with we need to implement a GNS algorithm inside this DGL for distributed training. But okay, so first, I really need to clarify that this GNS algorithm is only experimented in, is not really experimented in the distributed training scenario. It is only experimented in the case that we store the graph data in CPU and then use one GPU to perform the mini-batch training.
Okay.
Right?
I see.
So, but because this algorithm will really reduce the data movement, right? So it should work well on the distributed training case as well.
I see.
Right. So we should be, we should be able to, I mean, we should be easily combine all those methods together for distributed training.
Okay. And yeah, my second question is, can you explain like why GNS can reduce the time spent on the slice data? I understand like you try to reduce the GPU copy, but I don't quite understand why you can reduce the time for slicing data. Yeah.
Because the data is, I mean, we have data stored in the cache, GPU cache, right? So if any data that is already in the GPU cache, we do not need to copy them from CPU.
Yes.
So then we do not need to gather the data in CPU.
Yes.
So then there's no data copy in the CPU slicing. Is that what you're asking?
Oh, so yeah, maybe I'm confused with the orange part here and the red part here.
So the red part is that we need to copy data in CPU, because I mean originally the data is stored in a large tensor, and then we need to copy, I mean, slicing the data that is required for this mini batch.
Oh, okay.
And then we copy all the data into GPU. Right.
Okay, I think that's because it prefers sampling nodes in the cache, so they only require a little amount of nodes outside the cache, and the slice time was used to slice the features of those nodes. Because of the number of nodes required outside the cache was reduced, so the slice time was also reduced.
Right. So yeah, so I mean, this is basically the summary of these two work. I mean, overall, all our work trying to do is to reduce the data copy for the hybrid, either the distributed training setting or the hybrid CPU GPU training setting. And then we also need to worry about the load balancing issue, and we need to deal with the load balancing issue. And that's all.
Great.
Thank you. I think the lesson of data movement is all you need.
Yeah.
You want to write a paper like that?
Just before this talk, we were having a meeting about data movement, so could not be
okay.
time.
So yeah, actually I have some other questions. So
okay.
I'm wondering like how long is the matrix partition take in the first part, and how long is the GNS take in the second part? I mean, for the preprocessing.
We have the
yeah.
We have the number, right? So.
Or maybe I missed that.
Oh yeah, I mean like, so this is something. I mean, people keep asking, what is the overhead of the matrix partitioning and how scalable it is. So this experiment is that we want to partition the graph once. Partition the graph. Here, assume we partition a graph for every training.
Yeah.
Right, then depend on your training data, depend on your data set. So this we are experimenting benchmark those overhead of different components on this OGB papers 100M data set. This has like 100 million nodes and 3 billion edges.
Mm-hmm.
Actually, in this data set, among these 100 million nodes, only 1 million nodes has labels. So that means the training set is really small. So it's less than 1 million nodes because we use some nodes for testing, right? So that's why the training on this data set is very fast. Normally, if you have other data sets, your training cannot be that fast, even for the same graph size. But even for this case, I mean, like training takes 4 minutes, and then partition takes 12 minutes. But if you use different tasks like link prediction, then training becomes very slow.
I see. And how about the GNS? Does it take some extra overhead to do that or no?
So, I mean, training is GNN training, right? So, but this includes both the mini-batch sampling and the training.
Okay.
So we didn't really separate I didn't separate the training, the actual GNN computation time and the mini-batch sampling time.
Okay. I mean, for the later part, for the GNS, for the global neighbor sampling, you talk about, I mean, I'm wondering like, does that have some overhead to do that, or I know it's a must, but just wondering like, how much is the compute cost?
Compute cost? Do you mean?
I mean, how do you select the nodes storing cache, something like that?
Yeah.
Oh,
it's pretty minimal, I feel.
What is the? Sampling nodes into the cache is very small. Is very easy, right? The sampling probability is predefined, right? You follow the same sampling probability to sample nodes. Okay. I didn't notice any major very noticeable overhead in that.
I see. So maybe just one more question. So I feel like how to partition or how to sample nodes is a pretty important task for like large scale GNN training. So I'm wondering like, can you like train a graph neural network that can do the partition or that can do the neighbor sampling and to have a good performance, but also like fast?
Sorry, you train a Zheng model for partitioning?
Yeah.
Oh,
is that possible or
in the reverse order? I don't know. I haven't seen anyone, but I mean, we have seen people use a train GNN for clustering.
Okay.
This may be similar to what you are saying. I mean,
Yeah.
like if you run even but again, one thing is that partitioning is a little bit different from clustering, right? Partitioning want to enforce the balance, right? The number of nodes need to be the same, or number of edges need to be the same, right? Clustering,
Okay.
yeah. So it's I'm not sure. I haven't seen anyone who can use embedding based method for graph partitioning.
Okay. Just a random idea, yeah.
I think if you train a GNN for partitioning, then you need to run the GNN for partition before you train the GNN. So it's an egg and chicken problem.
No, I think if you can train a model, maybe you can apply to different data set like after.
Yeah, I know. I just mean, if you did that, I mean, use a GNN to partition, and before you do a real training, you need to partition, right? So you need to use GNN to do that. And how do we run that GNN?
I mean, running on a random partition graph.
Oh, maybe that's a bootstrapping.
Yeah, but that on the other, another thing is about sampling. So I don't think people will use a graph neural network to sample nodes, but there are work that trying to define a neural network to generate the sampling probability. So that is, I mean, this, I will say this is probably a very important direction to study a trainable sampling policy.
Yeah, thanks for the thoughts.
Okay, so I guess that's all for the presentation.
Great, thank you so much. Thanks again.
Thank you.
Thanks.
Welcome to Seattle when you have time.
Yeah, come visit us when you're here.
Sure. How is the COVID issue and the situation there
Well, I guess we'll see with the new variant, but everything's been, we've been coming into the building. So